Elements exist in three different phases: solid, liquid, and gas. The boundaries of these phases are best illustrated using phase diagrams. Phase diagrams allow us to predict the element's phase based on the temperature and pressure of its environment. The dividing lines are indicative of physical processes such as melting and boiling. At the boundary, the element experiences a fusion of the phases. Imagine an ice cube melting or water boiling. On the phase diagram, there exist two interesting points: the triple point and the critical point. The triple point, the intersection of all three phases, is the temperature and pressure at which the solid, liquid, and gaseous forms of a pure substance coexist in equilibrium. The particles of the substance are loosely arranged between the rigidity of a solid and the free movement of a gas. The critical point is the end point of the phase equilibrium curve between liquid and gas. Beyond this point, they're indistinguishable and form a supercritical fluid, which is a substance that behaves like a gas but still dissolves substances like liquids can. Supercritical fluids are useful because they allow us to extract one substance from another. In many ways, a supercritical fluid's function can be similar to that of water, a liquid solvent. For example, to extract an object's salt coating, we can coat the object in water to dissolve the salt, then boil the water to leave the salt behind. This works because salt and water evaporate at different temperatures and pressures. In the case of supercritical fluids, we can dissolve a substance, then lower the pressure to turn the supercritical fluids into gas. This causes previously dissolved particles of the substance to fall down for easy collection. Compared to regular liquids, supercritical fluids have the advantage of flowing more easily. This lets them quickly spread dissolved substances to make space for more, meaning they dissolve things faster. Because gas-like supercritical fluids are unaffected by surface tension, they can also get to spots that regular fluids can't get to. One application of supercritical fluids is the decaffeination of coffee. Previous decaffeination processes used dichloromethane, a chemical known to cause cancer. So coffee beans required treatment after decaffeination to ensure their safety. These processes also removed oils from the bean, ruining their taste and texture. Nowadays, we use supercritical CO2 instead. The CO2 passes over the coffee beans, dissolves their caffeine, then releases the caffeine once the pressure drops and the CO2 becomes gas. The bean's oil is left unchanged, and up to 95% of the caffeine is reclaimed for use in other products, like energy drinks or caffeine pills. Among other uses, supercritical fluids can extract proteins like diterpenes, antioxidants, and tetraterpenes, keratins. Supercritical CO2 can be used to extract vitamin E from fruits and vegetables, or even isolate floral fragrance from flowers. Near the critical point, substances rapidly fluctuate between liquid-like and vapor-like volumes, resulting in a cloudy appearance. This phenomenon, called critical opalescence, has fascinated scientists for centuries and has been observed in a series of substances, most popularly CO2. Scientists at Brown University recently observed the critical opalescence in liquid helium for the first time, suggesting that this phenomenon is universal. Here's a video of their experiment. We heat the liquid helium at about 4.2 K, and we can see the liquid start boiling. After about 5 minutes, the liquid level gradually disappears and the substance enters its supercritical phase. Then we stop heating the liquid when the temperature reaches 5.4 K. The liquid temperature lowers, and as it approaches the critical point, critical opalescence occurs at about 5.23 K. The fluid becomes cloudy because of the density fluctuation. As the temperature drops further, the liquid level reappears, indicating the phase separation between liquid and vapor. This video would make Albert Einstein very happy, since it helps prove the theory he proposed in his paper on the theory of opalescence.